The universe has long captivated us with its immense scales of distance and time. How far out does it stretch? Where does it end? And what lies beyond the star fields and the streams of galaxies that extend as far as telescopes can see? These questions are beginning to yield to a series of extraordinary new lines of investigation and to technologies that are letting us peer not only into the most distant realms of the cosmos, but at the behavior of matter and energy on the smallest of scales. Remarkably, our growing understanding of this kingdom of the ultra-tiny inside the nuclei of atoms is now enabling us to glimpse the answer to the ancient question: how large is the universe? In ancient times, most observers saw the stars as a sphere surrounding the Earth and as the home of deities. The Greeks were the first to see celestial events as phenomena, subject to human investigation, rather than the fickle whims of the gods. One philosopher and sky watcher named Anaxagoras suggested that meteors are made of materials found on Earth and therefore might have even come from the Earth. Those early astronomers built the foundations of modern science. But they would be shocked to see the discoveries being made by their counterparts today. The stars and planets that once harbored the gods are now seen as infinitesimal parts of a vast scaffolding of matter and energy that extends far out into space. Just how far began to emerge in the 1920s. Working at the huge new 100-inch Hooker telescope on California's Mount Wilson, astronomer Edwin Hubble, along with an assistant named Milt Humason, analyzed the light of fuzzy patches of sky, known then as nebulae. They showed that these were actually distant galaxies located far beyond our own. Hubble and Humason discovered that most of them are moving away from us. The farther out they looked, the faster these objects are receding. This fact, now known as Hubble's law, suggests that there must have been a time when the matter in all these galaxies was together in one place. Everything that astronomers saw in their increasingly large telescopes would have dated back to a singular beginning, now called the Big Bang. That the universe could expand had been predicted back in 1917 by Albert Einstein. Except that Einstein himself didn't believe it until he saw Hubble and Humason's evidence. Einstein's general theory of relativity suggested that galaxies could be moving apart because space itself is expanding. So when a photon gets blasted out from a distant star, it moves through a cosmic landscape that is getting larger and larger, increasing the distance it must travel to reach us. So how large the cosmos has gotten since the Big Bang depends on how long it's been growing, in addition to its expansion rate. Recent precision measurements gathered by the Hubble Space Telescope and other instruments have brought a consensus. that the universe dates back 13.7 billion years. In that time, a beam of light would have traveled 13.7 light years, or about 1.3 quadrillion kilometers. But taking into account the expansion of the universe, the most distant galaxies discovered by the Hubble Space Telescope are actually 46 billion light-years away from us in each direction, and almost 92 billion light-years from each other. So, is that the size of the universe? It's not, according to a dramatic new theory that describes the origins of the cosmos. It holds that our 92 billion light-year patch is a mere speck within the universe as a whole. The theory is based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposite charge, matter and antimatter. Back in the 1980s, the physicist Alan Guth proposed that energy fields embedded in the vacuum of space had suddenly tipped into a higher energy state, causing space and time to literally inflate. The universe went from atomic size to cosmological size within an infinitesimally short time. As a result, according to Guth's calculation, the universe as a whole would have grown to some 10 billion trillion times the size of the observable universe. That's a 10 followed by 24 zeros. Put another way, the whole universe is to the observable universe, as the observable universe is to an atom. The incredible fury of cosmic inflation helps explain the immense size and smoothness of the universe. But to succeed, the theory must also account for how the universe produced what we see around us. All those stars and galaxies and clusters of galaxies, and ultimately, us. Scientists are now attempting to piece together the chain of events that launched our universe in its earliest moments, by generating what you might call a little bang. At the Brookhaven National Lab in New York State, they are blasting gold atoms in opposite directions down tunnels almost 2.5 miles long. When these atoms reach velocities just short of the speed of light, they are sent into a violent collision. A fireball erupts, reaching a temperature exceeding 2 trillion degrees centigrade. As far as we know, the last time anything in our universe was that hot was about 1/1,000,000th of a second after its birth. What interests the scientists is the splatter of subatomic particles, a superhot soup of quarks and gluons that theory says gave rise to matter as we know it. In initial tests, this quark-gluon plasma has shown a crucial property: extremely low viscosity or resistance to flow. Scientists call it a perfect liquid. To grasp its importance, we go back to those primordial energy fields that the theory says spawned the Big Bang. The thinking is that those fields contain tiny fluctuations that were blown up to huge size during inflation. In the ultra-dense quark-gluon mix, These fluctuations generated pressure waves, or ripples. As the universe evolved, these ripples gave rise to variations in the density of matter. Amazingly, the imprint of those primordial ripples is out there today, in a faint signal discovered accidentally back in the 1960s. Working for the Bell Telephone Company, physicists Arno Penzias and Robert Wilson had built a giant horn-shaped antenna. But wherever they pointed, the contraption picked up excessive noise in the microwave portion of the electromagnetic spectrum. That noise turned out to match a prediction made years earlier, that in the wake of the Big Bang, the universe was filled with a cloud of extremely hot gas that scattered all light. As the universe cooled, the cloud dissipated. Light then shone through. Over time, the spectral signature of this light would have shifted as the universe expanded and cooled to what Penzias and Wilson detected. What they'd heard was the echo of the Big Bang. This image shows the smooth contours of the light recorded by the Bell team. Scientists would have to look closer to find the imprint of cosmic inflation. The Space Shuttle Discovery lifted the Hubble Space Telescope into orbit on April 24, 1990, in one of the most important scientific milestones of our time. Another launch, arguably just as important, took place 5 months earlier. The Cosmic Observation Background Explorer, COBE for short, was sent up to take a harder look at the microwave radiation discovered by Penzias and Wilson. The results came out 2.5 years later. The light of the early universe contained a pattern of hot and cold spots. In this image was nothing less than the origin of all we see around us today, smooth on a large scale, but with significant clumps, from which gravity would form gas clouds, then stars and galaxies. With this cosmic template in hand, astronomers set out to discover how the patterns and dimensions of the universe evolved over time. In an age of computer-controlled telescopes and automated observing, astronomers could now launch huge international collaborations with the goal of mapping a large fraction of the universe in 3 dimensions. At Apache Point in New Mexico, the Sloan Digital Sky Survey set the standard for mass production astronomy. A series of steel plates are drilled with holes that exactly match the location of galaxies in the night sky. After plugging fiber optic sensors into the holes, the plates capture the light of hundreds of galaxies per night. From that light, the astronomers calculate their distances from Earth. Another survey is named the 2-micron All-Sky Survey, or 2MASS, after the frequency of infrared light its detectors are tuned to capture. In this image, the 2MASS data covers a region 60 million light-years across. The local group of galaxies, including the Milky Way, are in the center. This is our intergalactic neighborhood. Jump further out to a region about 200 million light-years across. Our location is linked to the densely packed Virgo supercluster, the nearest intergalactic city. You can see the full breadth of our local region of the universe. Galaxies line up in walls and arcs. Beyond them are sparsely populated voids, the rural cosmic countryside. Moving out with the data, this region is over 650 million light-years across. Then almost 2 billion. 3.2 billion. And finally, out to a region 6.5 billion light-years from end to end, the cosmic continent. In the middle of it all, our galaxy, so immense from our earthly perspective, is less than a speck. The two-mass study, the Sloan Digital Sky Survey, and the 2-degree field in Australia have extended our maps to a quarter of the way back to the beginning of the universe. They have laid out a grand cosmic roadmap. COBE's successor, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched to scan the early universe for the fine-scale origins of this cosmic atlas. WMAP traveled beyond any interference from Earth to a position balanced between the Earth and the Sun. There, for 2 years, its detectors took in the pristine light of deep space. This is what WMAP saw. Tiny-scale structures that inflation would have laid out at the very birth of the cosmos. And a pattern consistent with the filaments and voids that had evolved in the universe at large. Scientists are poring over the WMAP data for clues to the true dimensions of the universe. One group, for example, looked for repeating patterns that could be evidence of pressure waves that ricocheted through the hot gas of early times. They saw none, which implies that the universe had grown so large during inflation that such waves could not cross it. Then they did the math and reported that the entire universe must have a minimum diameter of 78 billion light-years. So what is its maximum size? And what's beyond that? We will never know for sure what lies beyond our visual horizon, but astronomers are turning up some surprising hints in the universe they can see. To ancient observers, the universe was made of 5 classical elements: Earth, water, air, fire, and a 5th, quintessence, or space. Aristotle believed the stars, unchanging and incorruptible, were made of this 5th element. Today, we are finding that space, in fact, has a character of its own. Astronomers have calculated the gravitational pull needed to bind stars as they orbit a galaxy, or galaxies as they orbit a cluster of galaxies. They have found that there is simply nowhere near enough visible matter there to hold these structures together. The missing ingredient, its identity still unknown, they call dark matter. In supercomputer simulations of cosmic evolution, dark matter is added in to supply the gravitational tug needed to form the web pattern of filaments and walls, voids and dense clusters we see in the universe at large. But something else appears to be happening on these large scales. Astronomers have been making refined measurements of the cosmic expansion rate. They wanted to know if gravity was slowing down the pace at which the universe is growing. The markers they used, type 1a supernovae, are thought to burn at uniform intensities throughout the universe. By measuring changes in the brightness of these so-called standard candles at various distances, the researchers can spot changes in the cosmic expansion rate. To their surprise, the data showed that the universe as a whole is not only expanding, it's actually accelerating outward. The culprit is thought to be energy welling up from the vacuum of space, similar to what occurred in the early moments of the Big Bang, causing cosmic inflation. By emerging in minute quantities everywhere, it is pushing space outward across the whole universe. Over time, this so-called dark energy has grown to an astonishing 3/4 of all the matter and energy in the universe. With data like this pointing to an underlying dynamic within our universe, some scientists are thinking of the cosmos in far broader terms than ever before. There is a version of inflationary theory, for example, that suggests we live in one of many universes that may coexist side by side but do not touch one another. Like bubbles, they are continually rising up and expanding across the oceans of infinity. Just 500 years ago, in Galileo's time, many people looked out into space and saw a universe of lights centered on the Earth. The invention of the telescope revealed stars far from our planet. Then galaxies. Clusters of galaxies. And beyond them, vast walls and filaments of matter. Newer ideas about the size of the universe amount to a quantum leap in our sense of scale by extending these structures far, far beyond our horizon. Do these discoveries push us, on our tiny, out-of-the-way planet, into a smaller and smaller corner of creation? Or does our ability to comprehend and imagine the far limits of time and space somehow expand our importance in the grand scheme of things?